Hurry up, join.
Oh, hello. Still half asleep. And the best way to get around that is to do some exercise, like squats or push-ups or something. It helps get the blood flow. Or something really scary, make you fear that you have to run. Anybody else experiencing the whole the days going by like weirdly fast and you don't feel like you're getting as much done as you used to? The day split into two, other than nighttime and daytime, like awake time and a sleep time, or do you you take a nap in the middle of the day and then do something in the morning, do something in the afternoon?
I do a nap in the middle of the day.
Ah, I will admit I've done a few of those and they are nice. Yeah, I'll be starting in like a few minutes to give some more people some chances to join. I'm going to spend pretty much this entire video talking about how to do the Doppler equation. It's probably the hardest equation in the entire school year just because of understanding which way things are moving, but it's just because it's hard to contemplate in the beginning. Once you do it a few times, it's actually not that difficult.
Mr. Darling.
Yeah.
Oh, so like I've been split in two, as in like from like the time I wake up to like 12 or 1 when I stop doing work. is like that's like one part of the day, and then like for some reason the other part where it's just me doing me, it's like another part.
Oh, so it's like you have a job.
Oh,
You have your work time where you have to do your work stuff, and then when you're off work, you go and not do work.
yeah, pretty much.
Yeah, like I kind of warned you before you went off on this break. Um, whoa.
Sorry.
Uh, when you guys are going on this break, this is college basically. You are going to be given assignments. You are going to be given a task. You have a checklist of things you have to do, and it is on you to get it done. It's I'm not standing it over you in the classroom watching your work, saying, "Oh, did you mean to say that?" or "Oh, what did you mean by this?" I, it's not available as much, so it's on you to get the work done, and then go, "Huh, I need help," and then email me or message me or email a teacher. Thank you, Angel. Um, so yeah, it's one of those things. You're getting an early dose of living.
No, yeah, and then it's like split in two, and then like for some reason it goes faster when I'm doing work instead of faster when I'm like having fun.
No, that's actually the trick to doing like jobs that are really boring and monotonous. Like if you ever, like I worked J.C. Penney's and we had to stack shelves, or if you have to do like the cashier at a place, what you do is you do the work. You keep doing work, and the time goes by so much faster because you're just doing little things and just keeping yourself focused on them rather than going, wonder how much time has passed. I wonder what time it is. Is the time yet? I wonder what I have to get this done by the. It's one of those things that a lot of people who have like jobs that are very monotonous and very kind of repetitive. You just focus on the task you're doing, and then by next thing you know, it's over and you're out.
I've done that before when I would like help clean with my mom, but then like I'd be sweeping for what I felt like 3 hours, and it'd really be like 5 minutes.
Yeah, it's because you were focused on how long it took you, not what you were doing. Just be goal oriented. I need to finish sweeping this room.
Not really. I was focused on the stick of the broom, wondering if I could
Okay.
like really make it fly.
Oh, okay. Time's a weird thing conceptually for humans. All right. You don't have quite as many people in here this week as last week, but more are joining. But once again, this will be up on the YouTube channel at the end so that you guys can look at it and review. I really encourage you. I'm going to keep the chat up on the side of my screen as much as I can. To please message me if you have a question, or just pop into the audio channel and say, hey, I got a question. Let me know. Because while we're going to be doing a few calculations this week, and then next week's also going to be Doppler again, just to really spend time on it. A lot of people make simple mistakes with the equation, and that's why we want to spend a couple weeks just practicing it. And I want to make sure it's clear the first time. It's actually a concept that's not hard to understand. You've already done it, and I was reading through the answers from this morning. Most people did pretty well. A few people had a few misunderstandings on the shifting between frequency and wavelength, so we'll go over that as well. But of the people who did it, most of you guys were pretty close, if not completely right. And I remember I only graded on whether you got it done or not, whether you got it right or wrong, because that lets me know whether or not you actually, like, I now see, oh, okay, some people made mistakes with frequency and wavelength connection. Pretty much everyone got the truck one right from what I remember. But the answers are up on the screen right now if you need to. Okay, so let's start with what the Doppler effect is. It is an effect that you have heard all your life. Every single time a car drives by the school or your house or anywhere, especially if they are blaring sirens, you've heard it. You can hear that high-pitched as they're coming towards you, and then as they move away, it gets lower. And as you saw in the pictures, especially with the truck and such, and also if you went to the website, you can see the reason why is because as the thing that's making the sound moves forward, it catches up to its own wave. So here's a little visualization for that. So you can see I have here, so I have a bunch of circles. And just so you know, like this, let's say there's some object in the middle here that's making sound. So I'm going to make a little, oh, come on. There we go. Whoa. My drawing pad had a fun moment there. So let's say I just have a little speaker here. You know, he's making a sound. So that little speaker, get rid of some extra dots, is moving forward. When the speaker moves forward, the sound that it emits has to be centered on it. So it's going to move this little inner ring. If I can get it to select, it's going to move so it centers. Oops, someone's trying to get in. Let me get them in. Hello. Okay, going back. So it only moved a little bit, but you might notice that there's a slight change between this wavelength. Because on this drawing, in case you're wondering, the distance between, let's go with a different color to make it easier to see. The distance between each of these waves would be like a wavelength. So this would be your lambda. How many of these waves pass by my ear? So let's say like, this is my ear. How many of these waves pass by this ear is what I'll perceive as a frequency. Because remember, wavelength, ooh, let me actually spell out wave, is basically a distance or how far the wave is apart from each other. So it's that whole, like that's wavelength from here to here. Frequency is, I like to say it as how many in a second. So how many in a second? Because frequency can be more than just waves. If you've ever heard the term I frequent a place or I frequently do this, it's because you do that thing a lot. So if you ask for a frequency, it's saying how many of those things do you do in 1 second? Let's see. How come the plane high above sounds like a constant pitch? Oh, so like with a helicopter or an airplane comes over? Mostly because, I mean, if we're talking about like when the airplanes are landing, there is actually a very slight change in the pitch. But let me just try drawing this real quick out so you can kind of see. So if you are down here, and the airplane is way up here. Here's my little airplane. The sound it emits is going out. But it's moving at an angle to the angle you're at. So it's kind of a trig equation. Basically, the shift it makes is not going to shift these as close together. They're going to shift slightly right here. So there's a very slight change that comes closer if it's really far off, because the further off it is, the thinner the shallower this angle is right here. It's a trig function map. It's the reason why if you cross the street, you should cross at 90-degree angles. Because if you're in a car right here, you know, that was a terrible car. So here's my car from the top view, and here's a crosswalk. If a person was walking along here and went, oh, I'm just going to go diagonal this way, that actually takes a lot longer and is more annoying to the driver. If you had traveled, let's go green, straight here and then here and then here, even though your path is longer, to him, the displacement across his field of vision is much faster. Because from his field of vision, you went from this side to this side in, let's say, 2 seconds. But in the red one, you went from this side to this side in, say, 3.5 seconds. It took you a little longer, and that to him is like, oh, it's taking you longer to cross the street. In your perspective, you're like, oh, this is such a shorter distance. The airplane, because it's so much further away, and because it's coming at you at an angle, it doesn't shift the down distance here as much. It shifts this side distance more. Does that explain your answer, Daniel? Or your question? Okay, cool. So great concept. Actually, I don't think anybody's ever asked me that question in all the years I've been teaching. So way to go, Daniel. Really shows that you're thinking above the, outside the box on this one. or at least conceptually. So basically, this little scrunch here, and I'm gonna kind of exaggerate it. So I'm gonna move my sound source way over here. I'm gonna center this ring on where it is right now. I'm gonna center this ring on where it was a few seconds ago. Center this ring on where it was a few seconds ago, and so on. Now you can really see the scrunch happening here. As this sound source moved forward, the speaker, it's what it was supposed to be. I just can't draw very well. This speaker here moved forward. Every time it emitted a sound, it got a little bit closer to the sound wave that it had made before. Because remember, all sound waves travel at the same velocity in the same medium. That was on the brain genie you did. All these sound waves travel at the same velocity. On Earth, average, I mean, it kind of varies depending upon temperature, but speed of sound, so velocity of sound, is usually around 340 meters per second, up to 343 meters per second. It varies a little bit based upon temperature. Whenever you have to know the speed of sound, they will tell you, unless you're solving for it, and then they'll give you all the other information. But that sound source created another part of the wave. When it was a little bit closer, it caught up to that object, or the previous wave. So this right here, this part right here is going to have a higher pitch. Ooh, got someone coming in. 1 second. Okay. So that closer part is going to have a higher pitch. This further away part is going to have a lower pitch. We can even see if I like really squish this up. So that means this side sounds high. So when my ear passes by, I hit each wave sooner. I hit each crest sooner. That means I've hit more crests in a second. Frequency is how many in a second. So higher frequency, more frequency means higher pitch. When I get to the other side of the sound source, I hit fewer crests, fewer wavelengths, fewer waves, which means I have a lower frequency. I'm hearing a wave less frequently, which means a lower frequency. So that's the all right? Now, this is the part that tends to throw some people. The sound source moving can kind of make sense with this visual nice and easy. But if we instead make the person move through it, they also can experience the Doppler shift. I mean, that's when the ear was moving through. So like I can move it like this too. Right? Let's do this again, but this time with the ear standing still. Let me just make a couple circles real quick. And center that first one. Okay, so what if I make another ear? Let's make it red again so it sticks out. Okay, so here's my ear. This is my detector. This is what's hearing the sound. If this object is standing still, but I run through this, I'm going to hit sound wave 1, 2, 3, 4 pretty fast. And do remember, these sound waves aren't stationary. They are growing as we continue. So there's like a ripple in a pond. So these ripples on, let me box this, make this a little easier to see. I'm going to make this blue. So the ripples on this side of the wave are going this way, and the ripples on the green side are going that way. So when my ear travels into the blue side, the wave is coming to meet me. It's like tennis balls being thrown at me. They're going to hit me extra hard. They're going to be coming at me even faster than if I were standing still. So even though the source isn't moving, I am moving relative to the source. So I'm going to experience each of these waves faster than I would if I were just standing still. That means I'm going to hear that high pitch. Now I'm on the other side of the source. I'm moving with the sound waves. That means those sound waves are moving at 340 meters per second. And I gotta get the ear. And I'm playing catch up to them, which means I'm going to experience them less and less. It's like if I ran away from people throwing tennis balls at me, they'll hit me a lot less hard because I'm going with the velocity that they're going. So it'll be the here. So Doppler effect can happen when the source moves or the detector moves. Any questions on that before we get to the equation? I'll give you some time to type questions up while I draw a turtle. Okay, what happens if both the human and the car move at each other? Oh, then we get an even higher pitch, because if you think about it, if this source right here is moving in this direction and the ear is moving in that direction, then it's like two football players running into each other. I mean, think about it. If a football player crashes into a stationary football player, you hear a thud and you go, ooh, that was a good hit. But if two of them are running at each other full force and they hit each other, you go, oh, that hit even harder, because both of their velocities get to add up. So in this case, the ear would be traveling, ooh, didn't mean to draw on the ear. The ear will be moving this way, this will be moving this way, and it will experience the waves even more. And when it gets on the other side, now the waves are traveling away, so it will actually hear, you'll hear another drop, but here, again, even more so because the waves are getting stretched out by the source. Just so you know, this happens with light and sound. Even though the experience I'm talking about right now is sound, it happens also with light. We see this happen with stars. Let me just finish my turtle because I want him to see and have a happy face. There he is. Okay, so this also happens with stars. We experience this with stars a lot. It's actually how we know the universe is expanding. So if I have a star, this time I'm going to make a star like a real star. Yeah, I'm sorry, stars are a circular shape. I know that, you know, you drew them with pointed ends all the time. It's just an effect of the oh, red and blue light. Yep, Daniel's doing great. You're used to the sun always having like the twinkle twinkle effect, and that's actually because of our atmosphere, I'm sorry to say. But you know, we have, well, from our field of view, it's a fairly yellow sun. It's not actually yellow, it's kind of more red orange, it's orangish, but with our atmosphere, it looks yellow. Now, if we look at the color spectrum, so I have red, and the unofficial one is red, orange. That wasn't yet orange at all, was it? Didn't go to orange. There it goes. Red, orange, yellow. Come on. Green. Oh, I'll get to the why you see white in a second too. Let's see. Well, blue's good enough. We don't need the indigo violets, but I know that people think that there's purple. It's not actually purple. It's the roses are red, violets are blue. That's the violet. It's actually blue. But I want to make sure I read all three of these comments. Are most stars yellowish? Actually, I don't remember what the average star is. I think a lot of them are orange yellow. And as for when I look at this into the sun, I see it as white. Well, you shouldn't look into the sun. That's bad. It's very bright and will hurt your eyes. As for why you might see it white is because it actually does produce a white light. When I say that it's a yellow, orange or stuff, it's the chemicals inside of that burn. Like red giants burn colder. It's actually also a thermal degree. You ever heard of white hot? that's like when things are burning at an extremely high energy level. The energy level of our sun is around the middle. You can have stars that are right here that are very, 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 very hot, that are burning up and they don't live very long. And then you have ones that burn very slowly, and they're usually the red giants, the ones that are like 1,000 times bigger than our sun. But I drew this color scheme here just to kind of show you what's going on. Just like how sound waves pitch, do, re, mi, fa, sol, la, ti, do, have different notes, light for our eyeballs have different colors. So like with metal and extreme heat, yes, that's actually something that's called black body radiation, which is really neat if you ever go into physics. But really, it's just this. As it heats up, the molecules excite and they go flying off. Flying off molecules are particles, which are things we can see, which is how we see things anyways. So yeah, it turns red hot. It means it's glowing. It's reached the visible spectrum. There's a whole spectrum over here we can't see, and there's a whole spectrum over here we can't see. Over here, infrared, microwaves, radio waves, all that stuff. Over here, ultraviolet, X-ray, gamma ray, cosmic ray, much higher in frequencies. So like when it gets hot enough, it actually reaches a point where its energy output is visible to us. That's what it means. When you see something glowing from heat, you're able to visibly see the energy coming off of it. That's kind of freaking cool. Or in this case, very hot. But bad puns aside, I gotta make them now. I don't see you guys so much anymore. I kind of miss y'all. So like I don't get to make my bad jokes as much. So oh yeah, something can definitely glow blue. There's a difference between something glowing blue from its energy level getting high enough and glowing blue because the chemicals inside it. Like if you certain chemicals will burn blue because the energy they release is pretty high up there. I think sugar actually burns bluish. It burns very hot because it's got a lot of energy stored in it, which is why it makes us fat. Fire. Well, okay. Let's get the red and blue fire. There's two different types of differences: the temperature difference and also what's burning, because what's burning can change its color as well. Like I said, if you burn sugar, it burns bluish color. Like if you ever watch a video where they like light a donut on fire or something like that, with a Bunsen burner, tends to burn blue. Same thing with butane and propane. They burn bluish color in the middle because they burn hot, like hotter than normal fire. But if you notice, as it cools off or as it spreads out, you get more of the red on the outside. Don't cook the sugar, please. If you don't burn it right, it will smell horrible and carbonize, and it will just make your whole house smell, and your parents will be very upset because it will damage whatever thing you're cooking it in, because it gets caustic. Or not caustic, but it gets really nasty. It's how you make caramel, though, but you got to do it at the right temperature. But as for, wait, there was one about, don't just watch a YouTube video on it, okay? I don't want to condone saying, oh yeah, go out and burn something outside your house. Please don't do that to me. Don't make me feel like I'm worrying like about that. But there are certain chemicals that when they ignite, burn so hot. Like one that you guys shouldn't have around you much is phosphorus. Phosphorus burns so hot, it burns white hot. It can be used to usually start other chemical reactions that need super high level of heat. But the reason, let's see, I need to answer all the questions. In case something below glue. What about fire? Oh, and Esmeralda. Fire is actually a really interesting component because fire is actually just really, really fast rusting. Literally, it's oxidation. It is anything that can catch on fire is rusting at an extreme rate. It's just we mentally associate rust with iron or metal, but rust is oxidation and fire is rapid oxidation. It's kind of like the difference between blowing your breath over a hot food to cool it down or having an explosion occur. Both of them are rapid increases in pressure, you blowing out through your mouth, or an explosion, but one's much more destructive and happens faster. Okay, so anyways, getting back to the light source thing. So right here, I in the middle, we have ourselves, our yellow sun. Now, if our sun is rotating in this direction, so let's say it's rotating this way. Hopefully you can visualize that a little bit. It's going around that way. That means this side is moving towards us just a little bit faster than the center, right? It's moving towards us. That means the light on this side isn't going to be perfectly yellow. It's going to be squished a little bit because it's moving towards us. Now, if I go this way, I get higher frequency. So this is higher frequency. That means on this side, it's actually going to be what's called blue shifted. Even though green's the next one, we call the term blue shifted. So it's just going to be a very, very slight bluish color on this side. And then on the other side, it's going to be a very, very slight redder color because that side's moving away. So like I said, Doppler effect happens everywhere, light and sound in all kinds of waves. So as sources of things are moving, they change the frequency that's perceived. Like we know the universe is expanding because Hubble, when he measured the distance of a bunch of different stars, he noticed that all of the stars were red shifted. That means they were moving away. And as he observed them, the red shift got deeper and deeper and deeper red, which means it's going faster and faster and faster and faster away. Okay, so concept-wise, Doppler shift occurs whenever an object emitting a sound or a person who is listening or anything that can observe are moving relative to each other and making some sort of wave. Now, if you're wondering why we don't see this with light, that mostly has to do with the fact that we don't move fast enough to notice it. Like we as humans cannot run fast enough to cause a Doppler shift. The Flash should be blue shifted every single time they're running at you. So if the Flash was ever running at you because of how fast he runs, he should look blue. His red uniform should turn almost yellow, which is what the negative Flash is. So maybe that's why. Then the negative Flash would turn blue. So yeah. So fun little science facts. All right. Before I move on to the equation, any other questions? Just to give you some time to do that, I'm going to give my son the proper decorum that it deserves, like all sons. Oh, yes, you're right. You're right. In this day and age, he's going to need a mask. The son wants to be safe as well. Yeah, I've heard about several protests, and this is what happens when people don't actually do research. They're listening to a few sources of journalists that aren't giving proper information. They are having problems. But why does the sun need sunglasses? Because why are they called sunglasses if they weren't the sun's? I mean, you know, it's my jacket, so it's Aaron's jacket. It's the sunglasses. Also because he looks cool. I mean, he's super, super hot, so why wouldn't he want to look cool? Then it'll be called glasses. Well, they're the sun's glasses, right? Isn't that how you say it? Wah, wah, wah. Okay. Actually, because the mask looks like he has a weird, evil mustache. All right. Let's move on to the equation. What do we got here? Just to make sure. You just tried to like my comment. Okay, so well, this is what I said earlier. Doppler shift is when there is an apparent change in frequency due to the relative movement of the observer to the source. If you want to write that down as like some sort of definition to help you remember, but you can always Google search this and it will show up as the definition. It's like you can get it on Wikipedia even. And the Wikipedia page is actually pretty, are great sources of information. Just check the sources and, use the proper judgment. And you're going to move on to the equation because this is the meat and potatoes of it. This is the equation. I want you to notice something. I did not put any kind of math function here because the easiest way to do this equation is honestly, you change whether you put a plus or minus in these two places based upon whether you know that the pitch should go up or down. Even my college professors said, well, I could teach you the proper way with the vector coordinates and the calculations on them, but honestly, it's just a lot easier to go, should the pitch be going up or down? So I'm going to kind of give you a couple of examples and we'll do them together. So I'm going to draw a little person to make sure. Oh, went off a pen. There we go. So I have a sound source. It's a speaker on a tower. And I have myself. He's on a skateboard. Because I can't actually skateboard, so the me drawing can. And yes, he's going to be safe. He's going to have a helmet. Okay. So I've got me, and I got my skateboard. Let me make sure my chat is open. Close down for a second. Okay, so got me, got a skateboard, and I got a speaker with a sound source. If I am moving towards him, the frequency should go up, right? If I am moving towards him, the frequency should go up. This equation, if you haven't looked at the website, I probably should go over this right now. This is the frequency of the source. So this is Fs right here. This is the frequency detected. That is what I hear. This is what your ear hears. This is the velocity of sound. As I said before, velocity of sound is usually 340 meters per second, or sometimes it's 343. If it ever, whatever it is, it will be given to you. This here, velocity of the detector. This is how fast I am moving. This is velocity of the source. This is how fast the source is moving. Now, in this case, the source is a stationary pole. It's not moving, so that becomes a 0. But before you just cancel it out, let's make sure you understand what's going on. So if I am moving towards the source, the wavelengths are going to go down. The frequency is going to go up. If you look at the way this equation is set, it's saying, hey, some source is going to make a note. This thing in the parentheses is going to modify what this number becomes because it's this times whatever's in the parentheses. That's going to give me my new frequency. I know the frequency is going to be going up, so everything in here needs to be bigger than 1. Just to explain that, taking a side note here. Let me do different. So, just for a side note, if I had a number, let's say 5, and I want to know what this is going to be, and I multiply it by some y, if y is greater than 1, then 5 is going to get bigger. Makes sense, right? If y was 2, it becomes a 10. If y is 3, it becomes a 15. But what if y is less than 1? So if y is less than 1, if it's a fraction number, then 5 the x will become smaller, right? If y was 1/2, 1/2 of 5 is 2.5. Do you guys see how that works? Hoping if you see at any point you have a question, please hop in the chat, make a comment, or just pull up the video, pull up the voice. Okay. So if I know the frequency, if I know that the frequency I'm going to hear is higher than the frequency it's actually making, that means this top part needs to be bigger than the bottom part. Why? Well, remember when you guys do fractions? If I have a 10 up here, and I put a 2 down here, this becomes a number greater than 1, right? That's 5. But what if I put a 20 down here? Well, if the bottom is bigger, that becomes a fraction. If I want the frequency detected to be higher than the frequency source, or if I want the stuff I hear to be higher, the frequency to go up, I need to make the top bigger. So to make the top bigger, I have two math functions, add or subtract. Well, which one makes it bigger? Adding. I need to make the bottom bigger, or bottom smaller. Well, I can add or subtract, doesn't really matter because that's a 0. But this is the setup for this scenario. Give it a second to sink in and ask any questions on that, because I'm gonna give you a bunch of like scenarios before we put a number in this. Like I said, this is why it's kind of hard concept-wise, but it's so much easier than going, well, the vector this way is to the left, so I'm gonna make that the negative, but I'm making the sound going in the positive direction, you know. Okay, so just recap. If the frequency should go up, you need to make the top bigger. In fact, I'll write that in little in red over here. Better red, that's better red. If the frequency needs to go up, then top is bigger. If the frequency needs to go down, then bottom bigger. Do you see that? So let's go with a couple other scenarios and I'll walk you through it. So this time, I'm not gonna move. I'm just chilling on my skateboard because I don't know how to skate and I'm afraid I'm gonna fall off and break my leg. But for some weird reason, someone strapped a loudspeaker to a skateboard. And that skateboard is moving now. All right. If the sound source is traveling towards me, it's going to sound higher. Remember, it's like when the car is approaching you, the part. Well, if the frequency needs to go up, then the top needs to be bigger and the bottom needs to be smaller. Even though I changed what was moving, the equation's going to look the same. But when you put the numbers in, this one will be a 0 and this will be some number. That's why you got to make sure you have the subtract down here. Let's try another scenario. Let's say we're both moving. Let's say I am moving away and this one is moving away. So we're both moving away from each other. So if we're both moving away from each other, then these waves are going to take even longer to get over to me. That's going to go really negative, really slow waves. So that means, or really slow, low frequency. So if frequency goes down, then the bottom needs to be bigger. So the bottom needs to be a plus. I'm going in the opposite direction, so that needs to be a minus. We'll go through some scenarios to set it up, but I think it's the easiest way is, do I need the top to be bigger or do I need the bottom to be bigger? Do we need the frequency to go up or do I need the frequency to go down? If you're going in opposite directions, then make sure you use opposite signs. But what if we're going in the same direction, you ask? Well, let's say I'm being chased by this really weird speaker on a skateboard. Well, if I'm being chased, then this thing has to have some velocity. Let's put some numbers in just so you can kind of see. Let's say it's moving at 10 meters per second. Now, if I'm going slower, 5 meters per second, it's catching up to me. Yeah, chased by a siren head. I don't know what kind of weird dystopian future this is. I guess stuff mutated and now we have living sentient audio equipment. But as this sound speaker moves towards me, it's actually catching up to me. It's as if I were standing still and it's moving slowly to me, which means the frequency is going up and I would need to make the top bigger. But this gets a little confusing then, because if you want to make the top bigger, you would want to add, right? But if I make this direction positive, then I'm also going in the positive direction, right? Oh, wait, hold on. I got that. Now I make the top bigger. Sorry, I made a mistake. I want the top to be bigger, but the source is a bigger number. So here's a 10 and here's a 5. So, oh no, that would be right. So then, but if I add here, the bottom's going to be bigger than the top because this is going to be plus 10. That's going to be plus 5. If I subtract both, then this is going to go down by 5. This is going to go down by 10. The bottom is now smaller. I know it sounds really tricky, and you're not going to get a lot of these where both of them are moving. Most of them are just going to be one or the other. But that's how the math works. So I'm going to do an example question real quick. So let's go do a practice question. I'm going to use the same sources of sound. My speaker head guy on a skateboard, and then me on a skateboard. Safety helmet. Magic line appeared. All right, let's make up some scenarios. Let's do a pretty simple one. Let's say I'm not moving. So my velocity as the detector equals 0. Let's say the velocity of the siren is moving towards me. Velocity of the siren equals, let's go 20 meters per second. Let's say the frequency that it is emitting, let's give it a nice big number. Let's go with 1,000 hertz. And I want to know, what do I hear? And this is actually a list. Look, velocity source, velocity detected, frequency source, frequency detected. The only thing I'm missing is my speed of sound. Let's make speed of sound pretty simple. Let's say the speed of sound is 340 meters per second. So I just threw some numbers in. So this is my list. Well, the equation is frequency detected, oops, made an S there accidentally, equals frequency source times the velocities, VD is on top and VS is on the bottom. Okay, let's rewrite this with what we know. I don't know VD or FD, so that means FD stays unknown. F sub S is 1,000. I have a velocity of 340. I have a velocity of the detector as 0. I have 340 down here again. And then I have the velocity of the source at 20. Ooh, my drawing pad keeps trying to draw when I don't click on it. All right, let's think. Is the frequency going up or going down? Well, since it's moving towards me, that's the part, that's the high pitch. That means I need to make the top bigger. But if I add to 0, that's not going to make it bigger. I can add or subtract to 0, and it's not going to get any bigger because anything plus 0 and anything minus 0 is the same thing. Why is life hard? Oh, wait, I can change the bottom part. Remember, I just need to make the top one the bigger number. That means I can also shrink the bottom number. How do I shrink the bottom number? Well, I subtract it. So I'm actually going to do this with a calculator in front of you right now so we can go through this. But basically, I'm going to take the top part and actually let me get more space. So let me just get a little more space so I can draw out all the steps. So I'm just going to do this one step at a time. FD equals 1,000 hertz times, well, 340 meters per second over, well, what's 340 minus 20? 320 meters per second. Well, 340 divided by 320, it's going to be 1.0625. And that's still 1,000 hertz. Make sure you bring down your numbers and everything. And this is still in meters per second. Well, now I'm going to multiply these two together. So times 1,000 will get me a frequency detected of 1,600 and 1,062.5 hertz. Oh, sorry, actually, that's not in I made news. That's not in meters per second. And if you're wondering why, it's because they cancel out right there. Wondering why it ended up in hertz. That didn't seem right. Okay, so this is my answer. I'm going to leave it up there for a few seconds to so people can write it down. I know my handwriting's horrible, and I am sorry about that. But if you have any questions, like type it up now while I let people write this example down. And then we're going to do an example with me moving towards them. And then also with me moving away from them. Okay, just going to grab red real quick. Okay. I don't want to take the time to rewrite the whole thing because I want to make sure that I don't take your entire day and I don't know what else you have to do. But take a look at the equation of what we've done and imagine the scenario down here that instead of the sound source moving towards me, I was moving towards the sound source, but at the exact same velocity. So let's say in scenario 2, my velocity was 20 and its velocity was 0. Well, what happens up here? Okay, well, that means the 20 goes right here, and this becomes a 0. Well, does that change a whole lot? I mean, it's 380 over 340, which once I get my phone to unlock again, should show you it's the same number. I want to make sure you get the exact numbers. And you get a little bit higher number due to ratios, but it's pretty much the same thing. It's about 1 point, make sure I do it right. It's about 1.11 or so. So it's a little bit higher than this. Why? Well, because in this scenario, you're moving against the waves, and it means you get a little bit more hit into it. It's a small math thing, but they're pretty much the same thing. But yeah, you can see the math will still work out. You'll get a higher pitch. Okay, moving on to scenario or to section to 2 where I move away from him. So I'm gonna erase this and redo the away from him movement. If you didn't write something down, just remember this will be up on YouTube as soon as it emails me the recording, and then I can upload it. So we're going to keep pretty much the same scenarios, except this is not moving. Make this a little easier to visualize. It's not moving. I have a velocity of 20 meters per second, but away. So since I'm moving away, the sound should go down in frequency. That's like when the car is driving away from you. I could do this also with this guy moving away. It just it's the bottom part of the note. So let's try this again, but with this time, I know that I'm moving away. So if I'm moving away, the bottom needs to be bigger. So let's draw this out. FD equals 1,000 hertz, 340 meters per second. Now my velocity detected, how fast I am moving, because I am the detector, I have the ear hole, that gives me a 20 meters per second. And then down here, it's 0. All right. Well, I need to make the bottom bigger. How do I make the bottom bigger when it's a 0? I can add and subtract, it won't matter again. But I could also make the top smaller. If I make the top smaller, then this number, even though it's adding to a 0, becomes the bigger number. It'll become 320 divided by 340. So this becomes a fraction. How do we know it's a fraction? Because the numerator is smaller than the denominator. It's the top is less. It didn't make it all the way to 340. Remember, this is how a fraction works. It tried to make a full circle, but it only got that much of it done. It's missing that part right here. It's not a full circle. It didn't make it to one whole unit. All right, so if we plug that into a calculator real quick. We get 320 divided by 340, which gives me 0.94, let's just round it off to 1, times 1,000 hertz, which means that if I multiply 1,000 times this, I just move the decimal over 3 spaces, so I get my final frequency of 941 hertz. So you can see the sound goes down a bit. Now, once again, what happens if it was the sound source moving away and I was standing still? Well, that means the 20 would be on the bottom and the 0 would be on the top. You would want to add the bottom and subtract the top. That is pretty much it. That's how it works. Now, there's Brain Genie up already. That's due Friday. It's just 2 questions. It's all about this. Do your best. Next week, I'm going to give you just a worksheet with several questions on Doppler shifts and Doppler effects. And that's going to be more of this kind of practice where I'll need to see the steps. But like the Brain Genie is just, I want to see if you guys can figure out what the answer is based upon the questions in the multiple choice. All right. Does that make sense? Everyone feel good about this? Probably not, because like I said, this is one of the harder ones. That's why next week we're just doing more Doppler to make sure you understand this. Your questions of any kind that I might ask you more about concept, but like it's good to know how to do this kind of level of math, especially if any of you are going into planning to go to college or just to understand what a fraction means. Because if you're going to be a carpenter, you're going to be using fractions all the time when it comes to figuring out the exact ratio of how many square cubic feet or carpet you got, or whether or not the molding system is right. Trust me, I had to do this stuff. Seems to need to be, yeah, everyone, trust me on this. You're going to need more practice. That's okay. I am grading on attempt and completion, not correctness and ability. This is the practice time. This is the learning time. So if you need to go back to this video, please do. If you need to ask me questions, please do. You are absolutely allowed to take 82 attempts. Like, I mean, if you're just spamming through to get the points done, I mean, congratulations. You just kind of messed yourself over. You got those points. Yay. But that's the whole time reason for this. And you can message me and I will respond, and you can email me with questions. You can take a picture of the screen and send it to me and I will help you through it. So like, do not be afraid to ask me for help. This is like the hardest part of this whole like unit. And it's hard because it's getting that, well, should the frequency go up or down kind of concept. You had to go there, didn't you have to, Gustavo? You know the chat's recorded as well, along with the video. Or I guess I should probably, now. Anyways, so I hope you guys and girls are doing okay. And if you ever need to chat or talk or just like see me or something, please message me. In fact, let's get some actual FaceTime with you guys.